All right. So hello everyone. This is the second video in our series of tutorial on the use of ANSYS for electromagnetic simulations. And this particular one is dedicated to simulating the low frequency device. And as a low frequency device, I decided to show you how to simulate a transformer, because transformer is a very important device. No need to say, right, for importance of this one. So transformer, and we also gonna explore how to use the transient approach in the ANSYS. So as before, I start the project with introducing the Maxwell 3D design. Okay, and then as a solution type, I choose transient. Okay, I also already named my project transformer, and yeah, so as before, we start the project design with the drawing of the geometry, and our transformer gonna be rectangular shaped. So I draw the arbitrary rectangle, arbitrary box. Changes this name to maybe transformer. Let us material vacuum for now, and I change the material the geometric parameters. So the x size of my transformer gonna be LT, for example, x, right? And for now, let's put maybe something, so it's x, so it's a thickness of the of the box of the transformer. So let's put maybe, so first of all, I don't like to use the millimeters for this one, for this particular design, because maybe using inches would be more useful in this case. So in order to change the dimensions, I go to modular and then units, and then here for the units I can select in inches. Okay. Okay, so now this box is scaled automatically to inches, but I still need to give it some particular values, right? So for the L transformer X, I put something like 1 inches. For the L transformer Y, I put maybe 2 inches. And finally for the Z component of the transformer, I put maybe 2 inches as well. All right, and and the position. So I want my box, my transformer, the Z position to be 0, so it's in plane, and this 2 I changed to minus L transformer X over 2, and minus L1 transformer Y over 2, and let's click apply and see what we get. Click fit all. All right, so this is the body of of my future transformer. So next I need to I need to create the window, the 2 windows, and the limb, the central limb of the transformer. So I change the orientation of the grid to YZ. Next, I draw another box somewhere here, like this, and change the parameters of this box to maybe L core X, right? And so this is X. So let's make it slightly bigger than the thickness of the transformer body. So let's put it maybe 1.1 inches. So for the Y, so for the Y, let's put maybe something like Y divided by 4. So maybe something like 0.4 inches, 4 or 5, yeah. So the 2 inches divided by 5, so it's gonna be 0.4, maybe something like this. We can check that, we can change that later. And finally, for the Z size of the transformer, I put something like 1 inch. Okay, it's gonna be a box like this, and I of course need to change the position of it. So for the position, let's put maybe minus core X over 2. Okay, then minus L core Y over 2, and finally minus L core Z over 2. Apply. And change this sign here and here. Okay, so it's gonna be the window of my transformer, right? So what I do next, I copy and pass this box 2, and then I rotate this box around the axis Z, which is the vertical axis, by 180 degrees. Okay, and this way I got the second box, the second box oriented like this. So next I highlight the 3 boxes and do subtraction, Boolean subtraction, box 1 and box 2 from the transformer. Okay, click OK. So this is the core of my future transformer. So next I need to create the winding. Okay, and as a winding, I'm gonna first create a rectangle in the one of these windows, and then like rotate around this central limb, this rectangle. So this, I can draw a maybe a rectangle like this, something like this. So at this step, no need to be like very precise. So this is the cross section of my future winding, and now I need to create a path for this winding, for this cross section to go around the central limb. To do so, I draw another rectangle in the XY plane. Okay, so I draw the plane around my central limb, maybe something like this. Okay, and then change the position, the Z, in the vertical direction. So it's gonna be the half of the height of the transformer. So it's a 1 inch. Okay, so this this rectangle appears exactly in the center. All right, so now I can, for example, highlight this rectangle too, and then go to the modeler and delete last operation. Okay, so deleting the last operation in this case leaves only the edge of this rectangle over here. And now I want to, so maybe this rectangle is too large. I want to scale it so it's roughly, so it intersects with this with this rectangle over here. So in order to scale it, I can highlight it and then go to edit and scale. Okay, so let's put one here, one here, one here. And now I'm gonna change it in the X direction, maybe 0.9. Let's see what I get. And more importantly, in the Y direction, 0.9 Y direction, maybe even more, like this. Okay, so now this path and the rectangle intersect, and I also don't like that this rectangle is so large, so maybe scale this rectangle by a factor of in the Y direction. So let's put X back, but Y maybe something like this, or even more, like this, and shift it, move it along the Y direction, like this. Okay. So now I want to swap around this rectangle along this path over here. To do so, I highlight the path and this rectangle, and then go to draw and sweep along the path. Click OK, round 0, 0, click OK. All right, so it sweeps around this rectangle along the path and creates this nice body for the winding. Okay, so I can change the color of this winding to, for example, this copper like, and also the color of of the transformer to maybe something like this. Okay. So now I see that maybe now these two parts can intersect. So in my case, probably they don't intersect. Of course, I can check that intersection in the validation stage. So if I get something like valid boundaries, parts, yeah. So transformer and rectangle intersect. In order to fix that, I can also rescale the this winding along x direction, like make it just a little bit larger, maybe like this. Okay, so now if I validate it, so no intersection for this project anymore. All right, so next I can change the material of this winding to copper. Okay, to make it conducting. And now, since it's conducting, I can assign the winding by right-clicking excitations and then add winding. So in the transformer, in this case, for the transformer, I select voltage, stranded winding, and so our project is time domain, is transient. So I change the voltage to some voltage maximum, some amplitude times maybe sine, and 2 times pi times maybe 60 hertz and times time. So when you do time domain simulations in ANSYS, you write time in exactly this form. Otherwise, it wouldn't work. And also in this case, I also have to assign some resistance. Okay, and in this case, maybe 1 kilo ohm would be enough. Yes, and the voltage maximum, let's put maybe 120 volts. Okay, yeah, so this is the winding of our transformer. In order to use it, in order to excite this winding, I need to add the coil terminal, and as well as in our simulation of the eddy currents in the class, I use the same approach. So basically, I draw the rectangle, like a cross section of this winding somewhere here. Probably I need to change the orientation of the drawing. Okay, so this is the cross section of the winding, and I'm gonna assign the terminal to the coil terminal to this cross section. Okay, assign coil terminal, and let's put maybe something like 1000 conductors, which means the turns of the wire in the coil. Okay. So what's next? My my coil, my winding is ready, and I can. So the core is still made of vacuum, but let's have it made of vacuum for now. We also need to create the simulation region. So I click the simulation region over here, and then maybe create a region around with the size of maybe 20% of offset in all directions, and it creates perfectly this area around made of basically air. And for now I can hide it from the simulation. So what else? I can also add the solution setup, right? And solution setup in our case for the transient needs to add the stop time, right? So the simulation will be from 0 up to the stop time with the time step. So let's simulate our transformer from 0 second to 0.1 second with the time step of 0.002 maybe, and double check that this is second here and here. All right, so then I need to save all fields at every step. So I do every one step from 0 second up to 0.1 second with the step size that we indicated in the previous window. And then I double check that I have all these points in the sweep points. Close. Solver advanced. Oh, that's fine and okay. All right, the analysis is ready to run. I validate the project. Analysis setup. Currently, no mesh operations or data link have been created, so I need to create the mesh. And AD effect setting maybe need to revisiting. So yeah, I will add the AD current effects on the core, but for now the core is made of vacuum, right? So no need to add the AD currents, but the mesh, yeah, mesh is a good point. So for the global mesh, I put this this one over here in the mesh size in the middle, and or I can add this initial mesh settings also in the middle here, and add the local mesh to the winding, mesh operations, inside lengths. Okay, and of course maybe the box around also add the mesh operations inside length based. Okay, again, and now I can simulate this project, which is not the final one, but in order to see that the discretization of the time is selected properly, and double check that everything works properly, we can simulate this project, which is of course much simpler for simulation, because we didn't include the properties, actual properties of the transformer core. So let me put on pause the recording. All right, so this preliminary project is executed. I can go and see for example, the field distribution. For example, this magnetic field. distribution that our winding coil creates. And as we do so, we probably don't see any fields. In order to enable the fields, I need to change this time moment. So by default it says 0, and I need to change I need to select a particular time moment, for example 100 milliseconds, then click OK, and yes, so now I can see this magnetic field. So for now it's 1 millitesla, so very weak field, because we didn't insert the core yet. All right, and also I want to double check that when I create the transient report and do, for example, input voltage report, that my discretization of the time moments, of time instance, is sufficiently narrow, so I see the profile of the excitation wave, right? So this is the sinusoidal function that we use to drive our transformer. Right, so now we can change the parameters of the core, and again I go to the materials, edit, and as a material of this transformer I can select something like a material with a large magnetic permeability, magnetic permittivity, conductivity, magnetic varies. Permeability. All right, so here is the permeability. Let's use, for example, iron. So iron is not good material for transformers, but for the practice that's completely fine. So the iron gets a relative permeability of 4000, but also high bulk conductivity. Right, so I select iron, click OK. Okay, so now our core is made of iron, and is made of iron. What else? Let's double check that the project is validated. Yes, eddy currents, eddy effects. So I select the transformer and then assign excitation and set eddy effects. Okay, I include the transformer to the analysis. Okay. What else? Yeah, so that's basically it. I validate the project again. The check marks are all green, and I run the simulation again and pause the recording for now. All right, the project has been executed. It took maybe just 2 or 3 minutes. Again, we can check the magnetic field. Of course, we need to change the time. Yeah, so this way we can see that the magnetic core is it enhances the magnetic field. So for example, now the magnetic field somewhere here in this central limb of the transformer is around maybe 3-4 Tesla, which is much larger, like 1,000 times larger than before. Since this is the transient, we can animate the field, right? So to do so, I click this animate transformer or magnetic field, then click OK. Okay. It creates the frames. It takes some time. Almost there. Almost there. All right. So this is the animation of the magnetic field distribution in our project. 0. Let's put maybe yeah. So here is the animation of magnetic field. So more importantly, we can check the results, create the rectangular report, and create the report for induced voltage in the transformer and induced current in our first winding. Create. So yeah, this way we can calculate, for example, the amplitude of the current and amplitude of the voltage, and voltage induced current. And also in terms of fields, what would be important is to see the total loss or ohmic loss in the transformer, right? So because this is important characteristic, like when we design a transformer, in which parts of the transformer it gets heated mostly. So from this simulation, I see that this upper part of the transformer would heat more because the ohmic loss in watts per meter cubed, right, is the largest, is most significant. So so one would take care about like this area and maybe use some heating sink, some approaches to isolate use the thermal isolation, whatever. So this is the simulation of transformer with one single winding. Of course, any transformer contains at least two windings, right? So let us improve our design and include another winding. So the easiest way is to again copy and pass this first winding and then just rescale it in order to include, or in order to make it like around the first one. So I do edit, then scale, and next I definitely should make it a little bit larger in the X direction and also in Y direction, maybe more. So double check that they don't intersect. So in my case, it's still intersecting. Still 4. Very good. Okay. Yeah. So here is the second. It will be a winding, right? We need to create the new winding for the second one. So I highlight this second part and go right click the excitation and add winding. Again, I do stranded voltage, and for the voltage I do volts amplitude times. Let's do maybe amplitude. Let's do the same amplitude, and sine 2 times pi times 60 hertz times time. Voltage resistance, let's do maybe 0.1 kilo ohm. Okay. Again, next I need to draw the rectangle that will be used as a terminal. So for now I can hide this transformer core and draw the winding section over here, like this. Okay, and now I can right click on the winding 2 and assign coil terminal, and let's maybe add 100 turns in this case. Okay, so it's gonna be the second winding of our transformer. Next, I can get the transformer core back. So I see it. Okay, we validate the project. So it says that we need to change the AD effects. So no need to change them because we didn't change any material, any parts of this design that involve the AD current properties. Okay, so this is the transformer with 2 windings, the first one and the second one. So again, I can let's remove this all the results from the previous project and do the simulation. Let me put on the pause the recording. All right, the project has been executed, and yeah, it took me maybe about 5 minutes on my computer. So all right, so now we can see the results, and for the results we go to results, create transient report and rectangular plot. Okay, and here I want to see the induced voltages and currents in the first and second windings. So I can highlight this, choose this, select these 2 voltage input voltages, or yeah, induced voltages in the first and second winding, and create new report to see the voltage in the first winding shown in red and in the second winding shown in green, and the same plot. So apparently the voltage is different. For example, this peak voltage is different. Why? Because for the first coil we used 1000 turns, but for the second we used 100, so it's 10 times smaller, and also the induced voltage is also smaller, I guess, by a factor of 10. Again, we can check the current in the first and the second. And the current is reversed, right? So the current in the second winding is much larger than in the first one. And from this data, you can guess, estimate, or calculate the transformation coefficient of the transformer. Yes, so this is basically it. This is the simulation of low frequency device, such as a transformer. We learn how to calculate the induced voltages in the first and second windings. We learn how to calculate the magnetic fields and the losses in the core of this transformer. All right, thank you very much.